Hello, and welcome to another edition of our STM32 technical video series. Today we will be discussing calling the STM32's on-chip bootloader from your own user firmware. In a previous video, we've seen how the STM32's on-chip bootloader can be called using the boot 0 and boot 1 pins of the device. Application note 2606 discusses system memory boot mode. All STM32 devices can use the USART1 communications medium to communicate to the bootloader, and some newer devices such as the F2 and F4 families, the low power family, and the connectivity line can also use peripherals such as CAN and USB. Now, in addition to using the boot pins to map the system memory bootloader to the reset vector of the STM32, it's also possible to call the bootloader directly from your application firmware. This may be preferable if you don't have access to the boot pins. The boot 1 pin is used as a GPIO. Here we see table 21 in application note 2606. This shows each device family. Here's our STM32F4 family and the system memory bootloader starting address here at hex 1FFF0000. Different device families have different system memory addresses, so please consult the table or the flash programming manual for that family. In order to invoke the STM32 system memory bootloader, there are 5 things we must do. Shut down any running tasks, switch the clock source to the internal high-speed RC oscillator with no PLL used, disable all interrupts, and set the main stack pointer to the default value the bootloader uses. Then we load the program counter with the reset vector for the system memory bootloader, and away we go. Here we have the Kyle development environment and a simple program running on our STM32F4 evaluation board. If we halt our program, we can do a view memory operation and take a look at address 1FFF0000. As you may recall, this is where the system memory bootloader resides. If we look at the first word of memory, we see hex 20001000. This is the main stack pointer value that we're going to use. Now here we have a simple program toggling an LED at 100 milliseconds and reading a key switch. Upon key switch closure, we invoke our bootloader code snippet here. So the first thing we do is shut down any tasks running. We're not doing a lot, but we're going to reset our clocks to the default value. The bootloader uses the HSI clock. And then most importantly, we're going to turn off our SysTick timer, which the bootloader is also going to be using. So we'll set these 3 SysTick registers, control, load, and val to 0. Then we disable interrupts using the set primask function call. This is in the Kyle core_cmfunc.h header file, part of the SimSys library. Next, we're going to set the main stack pointer using the set MSP function call to our previously set RAM value here. And then we're going to point the sysmemBootJump function call here to our reset vector of the system memory bootloader. You'll notice this is the value we looked at plus an offset of 4, and this is because the first word is the stack pointer value, the next word is the reset vector. I've now attached my STM32F4 eval board to the USART1 COM port of my computer, which is actually through a USB bridge on COM 30 here. I press my wake up button on the eval board, which invokes the bootloader init function. I now press next. It's now readable and the bootloader is running. I can now go in, select the memory flavor I have, the 1 meg, and perform our various operations. upload and download code, do a mass erase. I hope you've enjoyed the video and learned a little bit more about the flexibility of the STM32's system memory bootloader. Thanks for watching.